Introduction to RTT and Bandwidth Delay Product. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will explore two fundamental concepts in network performance: round trip time, commonly abbreviated as RTT, and the bandwidth delay product, often referred to as BDP. These two concepts are absolutely essential for anyone working with networks, whether you are a network engineer, a cloud architect, or a developer optimizing application performance. Understanding RTT and bandwidth delay product is critical because they directly impact how efficiently data flows across networks. When you send a request to a server, RTT measures how long it takes for that request to travel to the server and for the response to return to you. The bandwidth delay product, on the other hand, tells you how much data can be in transit at any given moment across a network path. Together, these metrics help you understand why some network connections feel slow even when you have high bandwidth, why certain applications perform poorly over long distances, and how to optimize network configurations for maximum throughput. By the end of this presentation, you will have a solid understanding of both concepts and how they interact to affect network performance. Let me walk you through the diagram on this slide. The diagram illustrates the basic request-response cycle that forms the foundation of round-trip time measurement, starting with the client node, which represents any device initiating a network request such as your laptop, phone, or an application server. The client sends a request through the network, which is the interconnected infrastructure of routers, switches, and transmission media that carries your data. This request travels through the network and reaches the server, which is the destination system that will process your request. The server then generates a response that travels back through the network and finally returns to the client. This entire journey from client to server and back is what we call the round trip time. Measuring RTT with network tools. Now that we understand what RTT is, let us look at how we actually measure it in practice. There are several tools available on virtually every operating system that allow you to measure RTT to any destination on the internet. The most common tool for measuring RTT is the ping command. Ping uses the Internet Control Message Protocol, or ICMP, to send echo request packets to a destination and waits for echo reply packets to come back. When you run ping, it displays the RTT for each packet sent, along with statistics about packet loss and variation in response times. Let me explain the ping command shown on the slide. The command starts with ping followed by the -c flag, which specifies the count of packets to send. In this example, we set it to 4, meaning we will send exactly 4 ICMP echo request packets. The target is google.com, which is the destination we want to measure RTT to. Looking at the output, each line shows a reply from google.com. The ICMP_SEQ value indicates the sequence number of each packet, starting at 1 and incrementing for each subsequent packet. The TTL value, which stands for time to live, shows the remaining hop count when the packet reached our machine. A TTL of 117 suggests the packet traversed several network hops to reach us. The time value is what we are most interested in. It shows the RTT for each individual packet in milliseconds. In this example, we see times of 14.2 milliseconds, 13.8 milliseconds, 14.1 milliseconds, and 13.9 milliseconds. The final section shows the statistics summary. It tells us that 4 packets were transmitted and 4 packets were received, resulting in 0% packet loss, which indicates a healthy connection. The round-trip statistics show the minimum RTT was 13.8 milliseconds, the average was 14.0 milliseconds, the maximum was 14.2 milliseconds, and the standard deviation was 0.158 milliseconds. The low standard deviation tells us the connection is stable with consistent latency. The diagram illustrates the ICMP ping process. The client, which is your machine running the ping command, sends an ICMP echo request. This request travels through the network infrastructure, representing all the routers and links between you and the destination. The server at google.com receives the echo request and generates an ICMP echo reply. This reply travels back through the network infrastructure to your client. The time elapsed between sending the request and receiving the reply is the measured RTT that ping displays. Understanding bandwidth delay product. Now let us move on to the bandwidth delay product, or BDP. This concept is absolutely fundamental to understanding how to achieve optimal throughput on any network connection, yet it is often overlooked or misunderstood. The bandwidth delay product represents the maximum amount of data that can be in transit on a network path at any given instant. Think of a network link as a pipe. The bandwidth tells you how wide the pipe is, or how much data can flow through per second. The delay tells you how long the pipe is, or how long data takes to travel through it. The BDP tells you the total volume of the pipe, or how much data can fill it at once. Here is a helpful analogy. Imagine you have a water pipe that is 100 meters long and can carry 10 liters per second. If water takes 10 seconds to travel the full length of the pipe, then when the pipe is full, it contains 100 liters of water. Similarly, if you have a network link with 100 megabits per second bandwidth and 100 milliseconds of latency, the BDP tells you how many bits can be in flight at any moment. The BDP is calculated using a simple formula. BDP equals bandwidth multiplied by round-trip time. However, you must be careful with units. Bandwidth is typically measured in bits per second, while RTT is measured in seconds. The result gives you the BDP in bits, which you can then convert to bytes or larger units as needed. The diagram illustrates the pipe analogy for understanding bandwidth delay product. Starting with the sender, which represents the source of data transmission. Data enters the network pipe, which is visualized as a cylindrical tube carrying data. The pipe has two key properties: bandwidth, which determines how much data can enter the pipe per unit time, essentially the pipe diameter, and delay, which determines how long data takes to traverse the pipe, essentially the pipe length. The total capacity in transit represents the bandwidth delay product, showing all the data that can simultaneously exist within the pipe. Finally, the data reaches the receiver at the other end. The key insight is that to fully utilize the pipe, the sender must keep sending data to fill the entire pipe volume, which is exactly what the bandwidth delay product quantifies. BDP and TCP window size. The relationship between bandwidth delay product and TCP window size is one of the most important concepts in network performance optimization. TCP uses a sliding window mechanism to control how much data can be in transit before requiring acknowledgements, and the size of this window directly determines maximum throughput. TCP was originally designed with a 16-bit window size field, which limited the maximum window to 535 bytes. This was adequate for early networks with low bandwidth and short distances, but as networks became faster and spanned greater distances, this limitation became a serious bottleneck. RFC 1323 introduced window scaling, which allows the effective window size to grow much larger using a scale factor. Here is the critical relationship. If your TCP window size is smaller than the BDP, you cannot fully utilize the available bandwidth. The sender will be forced to stop and wait for acknowledgements before the pipe is full. This is like having a wide highway but only allowing a few cars on it at once. The road capacity is there, but you are not using it. Consider our earlier example with a 100 megabits per second link and 50 milliseconds RTT, giving a BDP of 625 kilobytes. If TCP uses the original maximum window of 64 kilobytes, the sender can only have 64 kilobytes in flight at any time. When the first packets reach the receiver and acknowledgements start coming back, the sender has already been idle, waiting. The effective throughput will be limited to 64 kilobytes divided by 0.05 seconds, which equals 1.28 megabytes per second, or about 10 megabits per second. That is only 10% of the available 100 megabits per second bandwidth. To achieve full throughput, the TCP window must be at least as large as the BDP. With a 625 kb window, the sender can continuously transmit while waiting for acknowledgements, keeping the pipe full at all times. The diagram on this slide shows the TCP sliding window mechanism and its relationship to BDP. The sender begins transmission, creating a flow into the data in flight region, which represents all packets currently traversing the network. This data in flight is bounded by the TCP window, which acts as a limit on outstanding unacknowledged data. The BDP threshold is shown as the critical comparison point. If the TCP window is smaller than BDP, marked as the underutilization condition, the network cannot achieve full throughput. The data eventually reaches the receiver, which generates acknowledgements that flow back to the sender. These acknowledgements free up window space, allowing more data to be sent. The key insight is that the window must equal or exceed BDP for optimal performance. Optimizing TCP for high BDP networks. When working with high bandwidth delay product networks, you need to tune your TCP settings to achieve optimal throughput. There are several key parameters that control TCP buffer sizes and window behavior. On Linux systems, the most important settings are the TCP buffer sizes, which are controlled through sysctl parameters. Let me walk through the commands shown on this slide. The first command displays the current TCP receive buffer settings. The sysctl command is used to read and modify kernel parameters at runtime. The net.ipv4.tcp_rmem parameter controls TCP receive buffer sizes. The output shows three values. 4096 is the minimum buffer size in bytes. 131,072, which is 128 kilobytes, is the default buffer size, and 6,291,456, which is 6 megabytes, is the maximum buffer size the kernel will automatically tune to. The second command displays TCP send buffer settings using net.ipv4.tcp_wmem. Like the receive buffers, this shows minimum, default, and maximum values. Having matching send and receive buffers helps ensure bidirectional traffic performs well. The third command shows how to check the maximum TCP window size using net.core.or mem_max. This is an absolute upper limit that caps the TCP_or mem maximum. If this value is too small, TCP cannot use larger windows even if TCP_or mem allows it. The fourth command modifies the maximum receive buffer to 16 megabits per second using the W flag with sys control to write the new value. This is necessary for very high BDP connections where you need window sizes larger than the default maximum. The fifth command sets the TCP receive memory values, specifying 4096 for minimum, 100485676, which is 1 megabyte for default, and 16777.216, which is 16 megabytes for maximum. These larger values allow TCP autotuning to grow the window big enough to fill high BDP pipes. The sixth command enables TCP window scaling using net.ipv4.tcp_window_scaling set to 1. This is usually enabled by default on modern systems, but it is worth verifying. Window scaling is essential for windows larger than 64 kilobytes. The diagram shows the TCP tuning decision flow, starting with high BDP network detected, representing the identification of a long fat network. The flow leads to calculate required BDP to determine the exact buffer sizes needed. Next is check current settings to compare against required values. Then increase buffer limits to modify our mem_max and wmem_max as needed. Following that is adjust TCP memory to set appropriate TCP_or_mem and TCP_wmem values. Enable window scaling ensures the TCP option is active. Verify with testing confirms the changes work as expected. Finally, Monitor performance, tracks ongoing throughput to validate improvements. Summary and key takeaways. Let us summarize what we have learned about round-trip time and bandwidth delay product and why these concepts matter for network performance. RTT measures the total time for a packet to travel from source to destination and back. It is influenced by geographic distance, network congestion, routing paths, and equipment processing. You can measure RTT using tools like ping and trace rotrot. Lower RTT means better responsiveness for interactive applications. BDP represents the maximum amount of data that can be in transit at any moment on a network path. It is calculated by multiplying bandwidth by RTT. Understanding BDP is essential for achieving maximum throughput because TCP window sizes must match or exceed BDP to fully utilize available bandwidth. For high bandwidth delay product networks, often called long-fat networks, standard TCP settings are usually insufficient. You need to increase TCP buffer sizes, ensure window scaling is enabled, and potentially adjust other TCP parameters. Without proper tuning, you may only achieve a fraction of the theoretical bandwidth. The practical implications are significant. When deploying applications across WAN networks, cloud environments, or satellite links, you must consider RTT and BDP. Network engineers should measure these values and tune systems accordingly. Application developers should understand that network performance depends on more than just bandwidth. The diagram provides a visual summary of the key concepts. Round-trip time measurement represents the foundation of understanding network latency. This connects to bandwidth delay product calculation, showing how round-trip time and bandwidth combine to determine pipe capacity. TCP window sizing demonstrates how TCP must be configured to match bandwidth delay product. Network performance represents the ultimate goal of optimal throughput. From there, monitoring and tuning shows the ongoing process of maintaining performance. The flow leads to best practices, representing the application of learned principles. Finally, optimized applications represents the end result where applications achieve their full potential on the network.